So for those who may be looking for a more note-based review, you want to see if you had concepts, if you have your concepts well down, if you have a concepts well known. A previous tutor from fall of 2023 did a very good review based on the notes part. So she has very good notes on this. I would recommend you go to the IEEE UTD YouTube channel and you'll find that there. And I think we can begin. So our first question is from all these questions that I'm going to cover for most part, as you can see, are from what you covered from exam 2 onwards up until the end of the semester. That's all I'll be covering for this review. So for our first question, it's communications one. So you have it. So there's a solution over here for those who may be interested to fact check me as I go on. So a 3-bit analog to digital converter is used to convert a signal that ranges from 3 volts to 15 volts. We are to determine the system resolution, the number of steps or levels or steps involved, the step size, the maximum quantization error, and the signal to quantization noise ratio. So for the first one, for a visual way to see this would be in our next question. So the system resolution is already given here. It means the number of bits that are used. So let's say if it said a 4-bit ADC, 5-bit ADC, that's what it's referring to as resolution. So given this, okay, I'll just hold on to that thought. I'll come to the next one to get to that question. That for the number of levels, or rather the number of steps, it'll be 2 to the power of the resolution, or rather to the number of bits. So 2 to the b, which is equals to 2. In this case, you have 3. It will be equals to 8. So essentially, looking a more visual way to look at it, and this question happens to be the same, happens to utilize that same concept. It has levels from 0 all the way to 7. So this, if you count from 0 to 7, those are 8 levels. So that will be the number of levels for this signal. The same as also in this conversion example. The step size, here it's asking for the size, this size right here. So if you do not have this graph and you just have the question, so you just go back to the question and see it's given you the range. So it has the lowest, so the 15 would be here, and this would be the 3 volts. So you have it where, I'll just delete this. Good, it's okay. I just wanted it to be in the same picture. So for the step size, you have the maximum 15 minus 3 over the number of levels. So over 3. And we have that here as 12 over 8. And you have that here as 1.5. So backtrack a little bit. So the resolution, just for the formality, it's the number of bits given in the question. The second question would most likely be the number of levels. The number of levels will be just 2 to that number, to the number of bits, which is 8 in this case. The step size, which is this, as it's also actually written over here, is the maximum voltage, the maximum range minus the smallest divided by the number of levels. So up to question 4, the maximum quantization error. So for this one, you just divide the step size by 2. So the concept or the reasoning behind this is that the quantization error will come about half of the step. It'll be around half of the step all the time. So that's why you divide by 2. So it's over here, 1 over 5 divided by 2. And on to question number 5, the signal to quantization noise ratio. So up until now, for this you've had to have done practice. So for question 5, we haven't used any formula yet. I mean, we have used a formula here, but this one's easy. Most of you have done it in Introduction to Digital Systems, so you know 2 to the power of something. But for question 1.5, there's a formula you have to know for this. So for this one, you can just go to the graph given and just check and see what you have. So our solution here provides us with 2 ways. Dr. Kogan usually taught us this way. It's an easier way. I'm pretty sure she also taught this other way, but she just touched on it because it's a more complex way and you have to keep a lot of variables into note. So we're just going to go with the one that professor used. So you have to know it's 1.76 plus 6.02 B. B representing the number of bits given in the question. So it's always helpful to read the question and get the data that you're given from the question. Because up until now, you may confuse and put in a different number. And there we go. So it's 1.7 plus 6.02. B, you just put in 3, and then you just do the calculation. For this one, we don't have to do it. It's already given. It's 19.82 decibels. And that solves that question. We'll get to, there's another question that can be asked about this, where you're given the signal, right? And then you're told to indicate these levels. So essentially, you just divide it by half. So, and mostly, let me see if I have another question like that. Yeah, I do have it here. We'll get to it. Let's go on to the next question. So this is not so much as a question, but you've seen this in the professor's slides for the spectral analysis of product of 2 cosines. This is applied in digital communication. So for those of you who are interested in the communication side of electrical engineering or computer engineering, you'll get to study more about this and why this is the case and why this happens. But up until now, we just need to understand this, the way it's drawn. So you need to understand that the one that's to the left is a minus. So minus FC meaning carrier. And M meaning message, as is indicated here. So it's minus 2 FC F carrier sub to the sub C, and then minus F to the sub M, and it goes on that way. So this is just something you have to visually look at it until you are able to understand it. Unless you're able to come up with a analogy to get it, you just have to pretty much just look at it. But this is not a question. I just put it there because we have another question that's going to depend on this. Understanding this to answer the questions. It also helps to understand that this too, so that this is a transmitted signal, the one in blue, and the one in purple is the received. Where is it? This one. So it helps to understand all that data that's given in the question. And you can find that in the slides. For this one, this is just generally the question we just did, but without both parts. So this one had this part, which is essentially this question drawn out. The professor or in the homework or in the exam, you can get just this question and you're told to answer this. So you ask for the resolution, you ask for the N, which is the number of levels. So it helps to know what these symbols stand for when you're doing your review. Number of levels, they will not always be given. They may be given, which in case they're given, you're in luck, but they may not be given. And if you don't know them, then you're confused and you may get the question wrong. For the delta means step size. QE standing for quantization error. Quantization error. And SQ and R just meaning the signal to noise ratio. Signal quantization noise ratio in decibels. So let's begin. So all the data we need is given in the question. So as you can see, the lowest point is minus 8 volts. The highest is 8. So for this one, we can't know the resolution, resolution directly. Sorry about that. We just have to count the number of levels we have. So for this one, it's pretty much the same as the one we had. It ranges from 0 all the way to 7. And if we count each level, all that amounts to 8. So we already have the number of levels, 8. So, right, so we know when going directly to the number of levels, when given the resolution, it's usually 2 to the number of bits, as the resolution means the number of bits, and it's equal to 8. So let's give this a 8. So this is a simpler one. So you just know 2 to the 3 is equals to an 8. But let's go. I don't think we're going to have any more a question complex than this. But let's say you're given a number like 2 to, you're given, say, 1020. I know you guys did a lab where you had to do this, but you had to quantize it to 1024. You had to do it to 16 levels. And those of you who did not do it to 16 levels did not get the full credit for that. I remember because I did not get the full credit. I wasn't able to make my signal using the potentiometer all the way to the other side and quantize it to the required levels. So you'd have to play around with math. So 2 to the b is 10 to the 24. So you'd have to do this to the same base. From either we've blend this to the same base, and then you just find b, it will be equals to what this number to the base 2 is equals to. And that's pretty much it. So to the step size, we know you have to do, so we already have the number of levels. The step size will be the most. So we have given the max here as 8 volts minus here, and including the signs, do not forget the sign, minus 8 divide by the number of levels. 16 over 8, which will be equal to 2. So the step size will be equal to 2. And as we can see, visually, the step size is equal to 2. So don't look at this. This might confuse you. If you go from -8 to -6, the difference there is 2. So you can see if you do it this way, there's a way to actually check yourself and see if you actually got it right. Delta quantization error. For the quantization error, we just divide the step size by 2. That's essentially, you don't have to like go into the whys and the whatnots. As I said, if you go further in communications, you're going to learn why that is the case. So 2 divided by 2, and the quantization error becomes 1. So let's go on. You have the signal to quantization noise ratio. For that, that's what I said. You've got to know the formula to this. It's 1.76 plus 6.02 being. So I've memorized this based on the fact that I did this exam before. So you got to memorize this. Even though it's just for the test, you got to memorize it. There's no way to cut short. And I don't think you're allowed a crib note sheet because you're taking the exam in the testing center. So definitely have to memorize this. And it is 1.76 plus 6.02. Remember the B stands for the resolution. So we already found the resolution to be equal to 3, and you'll be equal to 3, and then you just find the answer. And the answer should, since it's the same resolution, you should find the same answer as our first question based on the resolution. And that's pretty much it. For this one, I don't have the answers. So for those watching the video, you might do it and see if you got the same answers. And that will help you forward. And so for my exam, just to note forward, this question was on the test, so do not ignore it. The first 2 questions I've done are pretty much the same. The question that I'm going to do about this was on the test. Another very important question that was on the test is this, that requires you to actually really memorize. So for this one, what you essentially have you've seen this in digital communications, the digital communication slides. So you have it where you have a signal that's being sent. So this may be a signal, say, from someone calling you, from, say, your friend from, I don't know, home here. So the professor had a very good analogy on how to do this. So you have the message signal all the way as it's transported through the different mediums until it gets to the the recipient on the other end. So basically what you have to do is fill in what A, B, C, B, and all these other letters stand for. And this is a very important question. It's definitely going to be on the test. If you do not find it on, I'm not the one who's setting the exam. Sorry, I'm not saying that it's going to be on the test, but it's something to study for, since it has a lot of parts and definitely has more credit. So let's begin. And for this one, we don't have a formula to it, so you just have to memorize it. So A here is also for this question, if you do get to it, the way to answer this question on McGraw-Hill, if you've not done it before, is a bit tricky. So you answer it based on the numbers. So you have a drop-down menu on the end. I wasn't able to actually screenshot it because I don't have access to it anymore. But once you do get it, since I would recommend you ask for a paper from the people who are over there and get the numbers down. So A stands for what number given this drop-down menu. Don't just like, if you know A is equals to a certain thing, and then on the drop-down menu, because it's going to have all the numbers, then highlight that, but definitely do write down the numbers that are attached to each one. So A here is the input signal, or rather, no, the input message, this one. This will be A. And then the small a, or rather lowercase a, for the uppercase A will be the input inducer, transducer. And then B will be the message signal. I have a cheat sheet over here, so don't, it's hard to understand it. So, but since you're the ones who are going to do the exam, I would highly recommend you take your time understanding it. Then the next one we have is the carrier over here, which is that, and then we have transmitter. B is a transmitter. And y'all in the room can fact check me if you have access to the slides or if you remember. Then on to the next, D. So we covered the first one, second one, third one, fourth one, and the fifth, 2, 3, 4. And then D, we have transmitted signal. And then for C, we have the channel, uppercase C. And then for E, we have the received signal, E. And then we have, for D, it's the receiver, E. Then we have F is the output signal. Then E, uppercase E, is the output transducer. And then finally, we have G is output message. So this one was uppercase B, this one was lowercase c. Okay, so as you also, that can be a bit tricky. So this one was G. Can be a bit daunting if you fumble up in the middle, but a good way to look at it, since so that it can help you with the memory, is that for the first part, we have it as the input message. And definitely a G, we also need to have the output message. So, and for the first part is a transducer, it's the input transducer. And for E, we have the output transducer. And then for anything in between, you can just memorize it. On to the next question. So it's also about communications. So you're given a question saying that a periodic signal is a summation of sinusoids at 1400 hertz, 3400 hertz, and 2600 hertz. Determine the signal Nyquist frequency and an appropriate sampling frequency. So this student failed answering the signal's Nyquist frequency. So the signal's Nyquist frequency is twice its maximum frequency. So of all this that are given, so you're given 1400, 3400, you may get different values. So look at the one that's the highest. So for this student, I think they stopped at the highest, so it's supposed to be twice the highest. And the reason why this is to avoid a concept called aliasing. To avoid basically when sampling the signal, resampling the same signal. So it has to be higher than the Nyquist frequency. So the professor maybe said something like 10% higher than the twice the highest frequency. So, and that I think that's actually our next question. Considering both cost and quality of the following frequencies, the most appropriate sampling rate for this signal would be what? So that was a drop-down menu on this one, or those are a couple of questions given. So that actually makes it more tricky because so on this question, here's where you need to consider most. Here's where the real gist of the question is. You're considering both cost and quality. So for cost, if you get a super high level frequency, so you may have something like 10,000. That's pretty good for a sampling frequency, but that's very expensive. To get the hardware to make this, it will be very expensive. And quality, if you get something lower than, let's say 4,000 hertz, then that means you're going to lose on quality. So you need to look for the signal that's in between. And for this one, if you do get this question, you'll be given drop-down menu. So I would go through the process of elimination based on the answers that you're given. So you're given 10,000, you will see that that's pretty high. So you can keep that aside. 4,000, that's pretty low. How are you going to know 4,000 is low? Because twice the highest frequency in the question, 10% higher than that, is definitely not 4,000. So looking up to that, and the answer that was given in this case was 7,480 hertz. Any questions? If you have any questions, just raise your hand. So this is the question that I was actually talking about when I showed this figure over here. So the first time I saw this question, so we have the answers here. So this is another question I would actually recommend that you memorize or you understand, memorize, but first definitely understand. My pen is failing. Understand this distribution over here if you can. So it's asking us you're given the message signal at 14 cosine 2 pi 3000 t is transmitted using a carrier with a frequency of 1450 kilohertz. List the frequencies of the transmitted signal from smallest, which is the most negative, to the largest, most positive. So the first time I saw this question, I think I was in a hurry. I just went to this diagram and I looked to the most, see how it says most negative? Sorry for the going back. It says most negative to the most positive. So I went and took the most negative all the way to the most positive and did it this way. And I only ended up getting this two right. So I ended up fitting everything else. So that's why it's very helpful to read the question. And now with that motivation, let's read let's go. We're not going to read the whole question, but let's point out on the data that's given. So you're given the message signal. This is a message signal. And then you're told it is transmitted using a carrier with a frequency of 1450. So this is definitely the FM, this FC, right? And a simple, this is a very subtle point on the question, but notice it's in kilohertz, and the one that you're given here is not in kilohertz. So you're going to have to calculate the frequency here. This one is given only in hertz, and this one is given in kilohertz. So that's a subtle but very important difference. So let's first get the F sub m. So we know mostly in this intonation, it's usually given as A, amplitude, cosine, omega. That's omega, hopefully, or rather, which is a frequency, plus or minus the phase shift. That's the way that most of these signals are usually given. So for this one, we need to find this, and we don't need, this one is usually in radians per second. We need to find it in hertz. So what's the formula to that? Okay, so you have it as that is equals to 2 pi 3000. Okay, 3000. And we know that 2 pi over 2 pi over that b is usually equal to, actually it's not that. Usually has a thing, it's called b on here. It's just given the indentation b, but 2 pi over that is equal to the time. And we also know that 1 over time is equal to the frequency. So this is what we need. But we know if we take 2 pi over this, so 2 pi over 3000 is equal to the time. But we do not want the time. We want 1 over that. So how do we go about this? So we have the time. So it's essentially 1 over 2 pi, or rather, sorry, it's 2 pi over 2 pi over 3000. So you have 2 pi times 3000 over 2 pi. Those cancel off. So you have your frequency of 3000. So going back to that, I know I delayed a little bit. I may have lost some of you. So there's a formula on how to usually get the time given this over here, which is this formula, 2 pi over this b representing whatever is here is equal to the time, and 1 over time is equal to the frequency. If you do the math in between, usually 2 pi over that whole thing will be equal to 3000. So 3000 is given to us in hertz. And this was the difference I was recommending that we understand. So we have to convert it into kilohertz. So it's equal to 3 kilohertz. And 3 kilohertz here is our now this right here, FM. I know it's a bit messy, but I hope you're following. So we have FM as 3 kilohertz and the FC as 1450 kilohertz. So now we can actually now proceed with the question. So before you actually even go filling in the most negative frequency, next frequency, you have to first of all get those two values, because those are the two values that are going to be used in this question. And then now you have to have an understanding of what the transmitted frequencies are and what the demodulated frequencies are based on what the question is asking. So the transmitted frequencies are this right here. This formula might be worthy to write down, to note somewhere, to understand it, to look at it multiple times. And then you have the demodulated frequencies are this here. So this will be the answer to our first part, and this will be answer to A. This is the answer to B. Let's do one of them and see if we actually are correct. So for the most negative frequency, it will be given as FM plus FC. So minus 3 plus 1450 equal to minus 1453 kilohertz. So let's say you forgot to convert the kilohertz and you just went and did the math over here and you got the 3000, and because you're in a hurry or because you probably didn't know a question before and wasted time on it, you went directly and used the 3000, you end up getting this whole question wrong. Because you're going to use the 3000 and the 3000 is in hertz. And unlike your reviews, I know McGraw-Hill has this option where you can go on the homework, when you're doing the homework, you can go and see if you actually got the answer right? You have this option to go actually check the answer before you go on to the next question. You don't have that option on the test. So that's why it's very helpful to understand the concept in between. You have to convert the 3000 hertz to 3 kilohertz, and then use that to solve the question. Luckily, I did not make this mistake on the test. I ended up making it on the review, or rather on the questions that are given as the test practice. That's why I'm very much recommending and urging you that for you to take that practice test that's on McGraw-Hill. So let's do this one and see if we're gonna find the answer to that. So that's this. So they all follow each other. The first part, the second, so this will be I, yes, this will be that, and then this will be that, and then this will be IB. So this was for I. Let's do it for IB, or rather for Roman numerals. So that will be FM plus FC. And as you see, 3 plus 1450 will be equals to 1453. And that is the answer given here. And it should be the same for B. So for B, we have FM plus 2 FC. So minus 3 plus 2, FC being the carrier. And using I don't have a calculator with me at the moment, but once you do that, that should be what? 145. Not good at mental math. 145, 2, and be 8, 9. Is that right? Yeah. And then 0. So 2900 plus 3, and the whole thing negative. So it should be, need to put bars over here. So minus 2903. And that's what we're given here. And if you follow that process, then you'll be able to understand it. But the whole underlying knowledge behind this is to know how to convert, when you're given the message signal in this format, know how to convert it into the F sub M, and then know these formulas over here. You have to know this, and don't mistake one for the other. Don't use the first part for the second part. Don't use the first ones for the second one. So if you this question can help. So if you want to pause here, if you're looking on YouTube, just to get these formulas down. And also, if you're more of a visual learner, you can go back to this. It should be in your notes. You can also see it here. And yeah, but I don't think you can actually get to know that much here, because the question is actually asking for demodulated. Some of you, including myself, who has not taken a course on communication systems yet, you may not understand what demodulation is at the moment in a proper way, if you have not worked with that before. So moving on to our next question. So another communications one. So we have an analog to digital converter, uses 4 bits to quantize a signal that ranges from 19 to 5 volts. So this is the same question we had before. So we've seen this question 3 times now. So it might be helpful to actually go through it again just to reinforce what we learned. So we have the answers given here. So, and you also have the formulas given over here for those who may be interested. So let's go through it. So an ADC output will have how many levels? So this is what wasn't given, but based on the question, the one we had before had 3 bits. This one has 4 bits. So it's just 2 to that number, and 2 to the 4 is 16. So it has 16 levels. The levels being the different, so like if you're looking in the background, the level will be this, 16 of them. And then the output signal, we have a step size of, so for the step size, will be 16, or rather, no. So that's when we use the ranges given. It will be 19 x max minus x min, 19 minus 5 over the number of levels, 16. And if you do that math, it'll be 14 over 16, 2728. If you do divide that, you'll get 0.88 volts to 2 decimal places. Also, this might also be helpful in the question. It'll ask for a very specific range. So don't put 0.0889, don't put 0.9. Just make sure to look at the whole question on what it's asking for. The quantization error, is 0.88 divided by 2. So what you got before divided by 2. And as you might, if I am to pause at this, just to make this note, most of these questions follow a certain trend. So it's not going to ask for the SQ&R before it asks for the ADC, as you've seen now. So when you're going through these questions, just notice those patterns. So in case you forget, so you're reading it and you go blank, what the quantization error is, just know it's what you calculated before divided by 2. I know that's not the best way to look at this, but for the moment, that might be helpful since all these questions follow a certain trend to them. And then the SQ&R, this is where you need to know the formula 1.76 plus 6.02 number multiplied by the number of bits. So 1.76 plus 6.02 number of bits, which is 4 in this case. We do it this, wasn't a question. Then you'll find that the answer is 25.84. And it's also given here, the formulas are given here. The error is half the step size. The step size is this, ADC has that. Now on to our next question. So this is the question I was talking about. So the question will be, what will be the quantizer output? What will be the quantizer output for the sampled signal shown below? So for this one, for those who may not have understood what the professor is actually teaching, since it's by the end of the semester, you have finals coming up and whatnot, don't overthink it. Essentially, what it's asking for is a process which the professor showed in class, where you look where the signal is actually going in. Just look at where the signal is going in. Don't look at where all this is happening, where it's changing in between, and then it's going up, and then going down, down. Just look at where it initially, when it hits the boundaries, this being the boundaries, the dotted lines, vertical lines, when it gets to them, and then draw a line in between. And then when it gets to them, draw a line. And then go on to the next, and the next, and the next, and the next one, and the next one, so on, so on, so on. So where you draw the line, just go vertically, or rather horizontally to the number, and just write that number. So this one is on 4. Is on the row 4. This one is at 5. This one is at 4. This one is at 5. Within the row that's actually in, regardless of the level where it's actually is in, as long as it's in within the confines of the row, that's what the question is asking for. 6, 5, 4, 4, 3, 4. And then essentially what it's asking for is just to put in those numbers. So 4, 5, 4, 5, 6, 5, 4, 4, 3, 4. And for the last one here, it's still going. If let's say there's another added one over here. As I said, you don't have to worry about what it's doing over here. It can do whatever, as long as it gets into that column through that row. So here you still be 4, and that's what we have here. And that's essentially it for that question. So this is another slide that I thought was important. It may ask you, it may leave a blank. You may have this on the test, and it may leave a blank on what the analog to digital conversion process is. And since you did a lab on this, the professor may decide to ask you questions. And for those who are not here before, since I know some people joined us, as I said before, it's very helpful, very, very helpful to go through the reflection questions that you guys have been doing since actually the first day of class or the second day of class. Those questions will be examined